Okay, this should be a welcome back to Section 4, Chapter 5, as we've gone through the first few problems from this handout. I am now on problem number 4, and we're going to have kind of a calculator approach and by hand calculus approach. Optimal dimensions. You are planning to make an open rectangular box from an 8 by 15 piece of cardboard. So we start with this 15-inch by 8-inch piece of cardboard, and we're going to be cutting congruent squares from the corner. So we're going to go to our corners and we're going to cut out congruent squares of some size, and then it says, and then folding up the sides. So you get a pretty good feel for what's going on here. And our box, if we looked at it, would be box-like. We'd have something like that. So then it asks, what are the dimensions of the box of greatest volume? Well, when I fold all of these in on the dotted lines and fold this up, if I call this X and all the cuts are X by X, if I fold that up, then the height would be X, the length would be 15 minus 2 of those X's, and the width would be 8 minus 2 of those X's. So our volume, based on how far we cut in, would be length 15 minus 2x times width 8 minus 2x times height x. And kind of makes sense. What are the dimensions of the box of the largest volume based on how far we cut in x? So I'm going to go ahead and, now you need to understand right now, in fact, let's go ahead and do this with our calculator. We can get a little anticipatory solution here. I've already got that plotted in. Let's make this a little bit easier to see, darken things up. And here's our function. One thing that's nice to do on real world problems, oftentimes the domain is implied. In fact, I know that this function right here, after I superfoil it out, which we're going to end up, or after I foil and distribute it, which we're going to do, would end up, I'd have a, if I just multiply the x's, I get 4x squared times x. This is a positive 4x cubed. I already know that there are zeros at 0. There's a 0 at 4. There's a 0 at 7.5. And I know it's a positive cubic, so it wants to look something like that. But we may not be interested in the whole graph. In terms of this problem, this side 8 inches is going to have 2 x's cut out of it. X has to be less than 4. So 0 is less than x is less than 4. You could make an argument for less than or equal to, but if it's equal to, if it was equal to 4, we'd have no width. Therefore, our volume would be 0. If we didn't cut boxes out at all, and we said that x is 0, we'd have no height, so our volume would be 0. So I'm going to stick with 0 is less than x is less than 4. So when I go to graph this, darken this up again. When I go to graph this guy, I'm going to go window first, 0 to 4, and then I'm going to zoom fit. That is zoom 0. Just hit 0, and here's our zoom fit for this function. And I go second, this is that the height represents our volume, so second calculate that max is what we're looking for. Get to the left, get to the right, and we have 1.6, the period, oh, I thought I had that locked in here where we could see things a little bit better, sorry. So we have 1.6. It appears to be, it wants to be 1 2/3. So I'm going to suspect that this value over here is 5/3 something, I wonder. And 5/3 what? Well, I've got 90.741-ish. And that's straight from my calculator. Okay. All right, let's go through the calculus work that we'd have to do, though. That would be ultimately what we would be using to check. But we'll go through the calculus work here. Let's see what we got. I don't think I want to attack this with the derivative by using product rule, so I'm going to simplify this or multiply it out. Let's see, I would get 120. I would get minus 30x's, minus 16x's, minus 46x's, and I would get plus 4x squared all times x. Or volume based on x is 4x cubed minus 46x squared plus 120x. First derivative is 12x squared minus 92x plus 120. And if I set that equal to 0, when I set that equal to 0, I can divide by 4 and I get 3x squared minus 23x plus 30 equals 0. I need factors of 90, which add up to negative 23. Negative 5 and negative 18 get the job done. So I've got factors of, start with x minus 5/3 times x minus 6, but to get a 3x squared I need to multiply by 3, distribute it through, I get 3x minus 5 times x minus 6 equals 0. So x equals 5/3 as we suspected. Sorry, x equals 5/3 and 6, but 6 is out of our domain. So 5/3, what are the dimensions of the largest box volume you can make this way, and what is its volume? The dimensions. Well, the height would be x. It would be 5/3 x. The width or the length would be 15 minus 10/3, or 11 and 1/3. 11 and 2/3, excuse me. That's minus 3 1/3. We'd be subtracting 3 1/3 from 8 as well, and we get 4 and 2/3. I guess I could say by. So there's our dimensions, and what is our largest? What is the volume? Well, the volume is going to be V of 5/3. So V of 5/3, we'll go back to that guy. This is my y equals, so I'm going to kind of cheat on this, but I was going to use calculator anyway. My V of 5/3, we'd already gotten that, was approximately 90.741. So that would be our largest volume, and that is in, what units are we working in here? That's inches cubed. This would be inches. Okay, the best fencing plan. A rectangular plot of farmland will be bounded on one side by a river and on the other side by a single strand of electric fence. Rectangular, so something like this. If I call this A, I call this would have to be A, excuse me, and I'll introduce B here. We have 800 meters of wire, so I know that 2A plus B should be 800. It's easy, I think I know where we're headed. It's easy to solve that for B. B is 800 minus 2A. Now let's see what else we're looking for. Probably going to maximize area. What is the largest area you can enclose? Okay, well, I know that A could be really close to 0, but A cannot exceed 400, or actually can't make it to 400, otherwise there's nothing left for B. Okay. All right. So we are with 800 meters of wire at your disposal. What is the largest area? Well, our area in terms of A and B is just A times B. But since B is equal to this, B can be replaced by that, and I get area based just on length A is A times 800 minus 2A, or negative 2A squared plus 800A. Area based on A. Let's find its derivative. We know this is an upside down parabola, so a quick interpretation, we'd be maximizing volume at the vertex. So that is negative 4A plus 800. If we set that equal to 0, we quickly get A is 200. If A is 200, then B is 800 minus 400, 400 meters. And our maximum volume would be, maximum area, still back on the volume problem, would be negative 2 times 200 squared. Oh, you know what? Easier than that. Way easier than that. I'm going to go back to here, because I've already got A and B. Our area based on A and B, that was silly, is A's value, 200, times B's value, 400. So the maximum area is 4 times 2, 8 with 4 zeros, meters squared. Okay, there you have it. We'll be talking more about 5.4 problems. There'll be a section B along with this. Good luck.